So we have got 5-0. We may need, like, if someone asking a question or something, so that we can keep side. We can do a side one, like it appears like, yeah.
Wait, is that one?
Uh-huh.
You want me to
Yeah,
speaker.
exactly.
So who is speaking?
Right.
Who is asking that comes over here?
Correct.
Yeah. Yeah. Don't matter. So, but this will compromise your full screen. If you're not using this one, then the full screen will come on.
It's a bit small, isn't it?
So it is up to you.
Screen is better, I guess.
Now minimize that one. First one.
Yeah.
Then down to that's so visible screen is more. So you allow the recording?
Yeah, we will.
So allow recording.
Saurabh, you will record, right? Otherwise, I was thinking to record from this side.
Saurabh's recording request is already there.
Actually, I wanted to record for my purpose only.
Okay, okay. All right, so, yeah. I think we have more people in Zoom than at the room.
Recording in progress.
Got it.
What happened to your other student?
You're coming, sir.
Okay. What was what?
I was gonna fill this up and that's well.
So I like this.
I'm sure it's coming around and doing it.
It's not like that. Correct?
It's like the.
Good. Okay, can I come for this seminar and for volunteers? Okay. Maybe,
Recording stopped.
You can probably forward because if you want to ask any question, yeah, slightly forward to it. You can start now.
Yeah, I just want to check I can advance my. Sure.
Okay, so good morning, everyone.
Recording in progress.
In the room as well as in Zoom. So we have a series of 4 lectures by Professor Wilkinson from Oxford, and so is a world-leading expert on flavor physics, and was a former spokesperson of LSCB collaboration among many other hats you were. Yeah, so today we'll talk about where to study flavor and how to do it, and then obviously following the lectures. So that is.
Okay, good morning to those in the room and welcome to those on Zoom. I did a sound check earlier. I think you can hear me, but let us know if there's any problems. Okay, it's great to be here. I arrived yesterday evening and Gagad invited me to give this series of 4 lectures on experimental flavor physics. I'll also give a colloquium next week. For those of you who come along to that, I will have to some of this material I will repurpose, so I apologize if you see it twice. Maybe first, just so I get an idea of who I'm speaking to, I believe that most of you are PhD students, maybe there's a postdocs in the room as well. Some of you work on CMS, some of you work on Bell 2, some of you work on other things. Just so I can understand who I'm speaking to, would you mind putting your hand up if you work on Bell 2?
So people are on the Zoom.
Okay, it's the Bell 2. No, this is useful. It's not a test. I want to. What about CMS? Okay, and there's some theories here as well. Okay, and then there's experimentalists working on other things also, is there?
And some first year students.
Yes. Okay, right. No, this is helpful. Okay, so right, and I guess the people on Zoom, I won't ask you to put your hands up, but probably you are split in a similar manner. Okay, so I've been asked to give 4 lectures. My experience of giving lectures in Oxford is usually that there's a decent number turn out for the first lecture, and then there's an exponential decay as things go on. So we'll find out what the decay constant is. But I will. I've been asked. This is a 90-minute slot. I certainly will not be talking for 90 minutes. I will talk for about 50 minutes. But the time after that, I'm very happy to hang around and discuss. Also, I'm very happy to be interrupted. If anything is unclear and you want to ask me in real time, that's absolutely fine. So don't be shy. Right. So I'm going to talk about flavor physics. As Gagan said, I'm involved in flavor physics on several experiments, but mostly I've been involved in LHCb at CERN. So in these 4 lectures, I'm going to cover this. Today's lecture will be very much introductory. Very briefly, I will remind you why we should care about flavor physics, but then where should we study this? As I say, there's various facilities where we can do this. A very important one is E+, E-, and Bell 2 is the front runner here at present. I will talk about this, but I should apologize at the outset. I will be focusing on hadron machines. This is my background. My slides are actually repurposed from a series of lectures I gave specifically on hadron machines. So I want to try and tell you, why hadron machines are very good for flavor physics. And then something which is maybe not obvious to everybody is why you need a dedicated experiment, why you cannot just do the flavor physics program at Atlas and CMS. Why do you need LHCb? So today's lecture will be introductory. It will be partly historical because I think history is interesting, and history also tells us answers some of these questions. But we should still focus on some physics topic. So at the end of today, I'm going to focus on something which is not actually flavour physics, but something that we do at flavour physics facilities, which is hadron spectroscopy. So I'll devote some slides to that. Tomorrow, if you turn up, and I hope you do, we will then focus on one of the very main topics of flavour physics, which is unitarity triangle and CP violation measurements. So this is a very rich and beautiful area of science, which I hope to do justice to. Next week, I will then look at flavour changing neutral currents. These are suppressed, very rare processes which are highly sensitive to the presence of new physics particles. And then in the concluding lecture, we will look at charm physics, because in lectures 2 and 3, we'll be talking mainly about B physics. And I will also devote that lecture to future prospects for these areas of studies. And as already admitted, I'm going to be talking, a lot of my examples will come from LHCb, but I hope the discussion is more general. Okay? Right, so I must learn to use this keyboard, not that one. Okay, so this is the road plan for today's lecture. So let's get going. So firstly, very briefly, and this is something I will elaborate on more in the colloquium next week if you turn up. Well, why should we care about flavour physics? Well, it's a puzzle of the standard model. It encompasses many of the open questions. Actually, most of the pre-parameters in the standard model are, in some sense, flavour parameters. So look, some of the open questions I could point at which are related to flavour is why are there 3 generations of quarks, and why this extreme hierarchy of masses? The up and down quarks weigh virtually nothing. The top quark is essentially the same mass as a gold nucleus. The CKM matrix, this has a very, very distinctive hierarchy. The diagonal terms are essentially unitary. As you go off the diagonal, they drop away dramatically. What is causing this hierarchy? This cannot be by chance. And then the mystery of CP violation. So the CKM paradigm, because this matrix has a complex phase, it can accommodate CP violation, but I don't think it really explains it. Furthermore, if you look at flavour, in particular quark flavour, because I'm going to be focusing on quarks, can we learn anything about the matter-antimatter asymmetry of the universe, which most theorists would agree really cannot be trivially explained within the CKM paradigm. So these are already questions in the standard model itself. And if we go beyond the standard model, flavour is a tool of discovery. So in flavour physics, what is our guiding principle? Our guiding principle is to probe processes which are driven by loop diagrams. And here you see a bunch of diagrams. Each of these has a loop involving virtual particles. And why are we interested in these? Well, these are here drawn with their standard model particles in the loop, but in these loop processes, which are generally suppressed, non-standard particles can also contribute, here shown by the question marks, and these contributions could perturb the amplitudes and lead to measurable effects above the predictions of the standard model. So if we make precise measurements, we can be sensitive to this. And this is the indirect search principle, that precise measurements of phenomena at low energies, because we'll be generally talking about B decays and charm decays. These are rather low energy processes. These will tell us about unknown physics at potentially much higher energies, because these new particles could be very massive indeed. Okay, so my lectures will address how these measurements are made. I'm going to focus on colliders. One can make measurements like of rare lepton decays, not using colliders, for example. And I'm going to be focusing on quarks, and these are heavy quarks, charm and beauty. This is selective because there is still much we can learn from kaons, and the mysteries of the flavour extend to the lepton sector also, but there's only so much I can talk about in these 4 lectures. Right, so if we are talking about colliders and studying these physics, where can we do this? So this is a table I assembled on my plane journey out yesterday. Three essential places you can do this. One in E plus, E minus, at high energy when you produce Z zeros, and the Z zeros will decay. They decay hydronically. About 20% of the time they will decay to BB bar. And this means you can carry out a nice program of B physics if you have a machine which runs at the Z zero. We had such a machine that was lit, and these experiments made very nice pioneering measurements in the 1990s. There's no such current machine doing this, but one is proposed for the future, and I will talk about that in my final lecture. Then you have the possibility of running an E plus E minus machine at threshold. So if we concentrate on the beauty case, this means running at the epsilon 4s, where you produce BB bar and nothing else. This was already realized way back in the 80s. Argus and Clio ran there at the start of this millennium. Barbar and Bell did, and now we have Bell 2. This is a very beautiful way to do B physics, and I'll talk about that, and it has a future associated with it also. And then you have the Hadron Colliders. So the work started here back at CERN in the 1980s with the SPP bar S and measurements made by UA1 and UA2. These were continued at Tevatron, and now they are happening at the LHC. So I'm going to focus, as warned. Oh yeah, please just say.
No, previous slide. Why not at site 3.1, Z side resonance? Why at site 3770?
Oh, no, right, because, yeah, so people, let me repeat the question for people on Zoom. The question was, E plus E minus, why, for the charm physics, right one at 3770, not at the J side. And that is, yeah, my focus is on flavor physics, which is probing the weak decays of beauty and charm mesons. So at the J psi, you don't get open charm produced. The J psi is a very interesting system to look at, also from the point of view of spectroscopy, but you don't get two D mesons produced. And to do what I call core flavor physics, you'd like the BB bar mesons, and that's why you go up higher in energy. And that's why for the BB bar you run at the epsilon 4s, any resonance below that, you don't produce BB bar. Okay, thank you.
So this thing, E plus minus to Z to BB and 4s to BB bar. So I was confused why there are two separate experiments basically handling these final states, but the middle particle is Z and the another case is 4s. Why it's there? Is it the energy range?
Right, okay, so the question is just, again, for people on Zoom, why is there this, we distinguish between these two columns, the left one with the Z0, the right column with the epsilon 4s. Yes, it's energy. So the epsilon 4s lives at something like 10 GeV, and the Z0 is 91 GeV. So this needs a completely different facility, and it needs different detectors. Okay, so I'll talk a bit about this today. But the Z0 case, that we won't come back until to that until the fourth lecture. Okay, right, great. So let's continue. Right. So firstly, you know, so talking firstly about the epsilon 4s. So that was my middle column. What is attractive about doing B physics here? So there are several advantageous features. One is that you're producing the BB bar at threshold, so you just have a B meson and a BB bar and a B bar meson, and you have nothing else. You have no fragmentation particles. This is to be contrasted with the Z0, which I'm not talking about, when you actually get a lot produced. So this means that what you can do, if you want, you can actually reconstruct the whole event. You can look at each every particle in the event, and you can assign it to the decay of a B meson. And this is very nice, particularly if you're trying to look at a B meson which involves a neutral an undetectable particle, such as a neutrino. So this is an example, B to tau neutrino. If you want to infer the existence of this, what you can do is you can reconstruct what you can in the tau decay, so here an electron, and you can reconstruct everything else in the event, so the other B, which is in this case decaying fully hadronically to particles you can reconstruct. And therefore there's missing energy and missing momentum, and because you know the actual energy of the initial state, you can infer the presence of the neutrino, and you can say with high confidence that this decay has been produced. And the decay of this sort's of great interest. So this is essentially the only place you can reconstruct such a decay. Another example like this, which is very, very topical, is B going to K nu bar, so B with two neutrinos. And I say this is topical because Bell 2, maybe we'll mention this on next week, but at the recent EPS conference in Hamburg, they announced the first observation of this very rare decay, B to K nu bar, and it was actually seen at a surprisingly high rate. The branching ratio was about 3 sigma above the standard model. So this is already exciting a lot of interest, but you can only reconstruct such a decay at such a machine, right? Because of the problem of knowing whether they're neutrinos or not.
And question.
Yes.
So in this case, so you can reconstruct completely like the white forest.
Yes.
So the case is here, so it's fully coverage detector because usually the forward region of the detectors are not covered. The Z component of the neutrino, the momentum of this neutrino of the Z component is not recoverable completely.
Right. So the question was, to what degree can you fully reconstruct this because the detector does not have full coverage? And you're right, because there's regions near where the beam pipe, where charged particles or neutral particles could go. So yes. So the analysis is not trivial. You have to select events where you believe that the two Bs are decaying in the barrel region. So you have to, as best you can, exclude those regions, but you have to account for that possibility in the assignment of your systematic uncertainties. Yeah, so it's harder to do than I'm saying here, but it still can be done well enough. Okay, so another reason why this is a nice place to do B physics is because you're at a low multiplicity environment. As I said, there's very few tracks. There's no additional tracks apart from those produced in the BB bar decays. This is to be contrasted with the hadron colliders I'll talk about shortly. But the fact is you don't have lots of additional particles. It means that things like pi zeros, ethers, photons, these things where in the hadron machines you just have enormous numbers of them. Here you have rather few of them, so you can actually do a very good job in reconstructing final states with such decays in them. Okay, these particles are easy to handle in a low multiplicity environment, less so in a high multiplicity environment. Also, long-lived particles such as K shorts and K longs, they're just easier to deal with in these rather clean decays. And there are a lot of decays which contain such particles, and so this is important. Decays such as D0 to gamma gamma or B0 to pi 0, this is really the only place you can have any hope of reconstructing them. And then finally, this last point will need a bit more elaboration, so I won't fully explain it here, but I want to flag it up for you because we will talk about this in lecture 2. If you want to do time-dependent CP violation, you have to do something called flavor tagging, and beware. Flavor tagging, actually in flavor physics, means something different to what you're used to if you're doing like Higgs physics at CMS. There's a distinction between flavor tagging for time-dependent CP violation measurements, which means trying to identify the flavor of the V0 when it's produced, and when you compare to if you talk about tagging the flavor of a Higgs jet. I will explain this, I hope, well tomorrow. All I want to say is actually the epsilon 4s, you can do this much, much better. And that's due to actually a beautiful quantum physics effect, which is that the B and the B bar are entangled. And therefore the one B does not start to mix until the other B decays. And this has the practical consequence that this tagging works much better at the epsilon 4s. So this is a subtle point. Let's talk about it tomorrow, but an important one. So I've told you why the epsilon 4s is great, and indeed there were these experiments, Barbar and Bell, in the first decade of the millennium. They were very successful. Their observation of CP violation in the B system essentially led to the award of the Nobel Prize for Kobayashi and Mascara. So you'd like to carry on doing physics like this, and indeed the Bell 2 experiment running at KEK at present is just such a facility. So this has already collected about as much luminosity as the Barbar experiment did. It's in shutdown. It will come out of shutdown at the end of this year. The idea is it will collect much, much more luminosity, about 2 orders of magnitude more. So it's got a long way to go, but it has very rich prospects, and we'll talk about those prospects next week. Right, so epsilon 4s is a great place to do B physics. Why would you want to go anywhere else? Just to emphasize that very point, I talked about the low multiplicity environment. Here you actually see an event display on the left, which is an epsilon 4s event display. So you just see here these 2 B's decaying. You see that there is not much happening. There's only a few tracks in the event. By eye, you can see what those tracks are. It's beautiful, it's pristine. On the right, you have an event display from CMS with, I don't know, probably 30 piled up interactions, and this is absolutely disgusting. So really, it's a no-brainer. You'd like to work in on the left-hand side environment, not the right-hand side. And I've talked about all the other advantages of the epsilon 4s. I don't need to relabour them here. So why on earth would you want to do B physics at the LHC? There are advantages, and these advantages are significant. The cross-section for BB bar production is much, much higher. It's a nanobarn at the epsilon 4s. At the LHC, it's 600 mu barn. So this is orders of magnitude higher. So even though the luminosity of the E plus E minus machines are in principle very high, in terms of number of BB bars produced, you get a hugely large, many, many more produced at the LHC. You get all hadron, you get all B hadron species produced. If you're at the epsilon 4s, you just have B zeros and B pluses, and obviously the CP conjugates of those. If you're at the LHC, you will also get B sub S's produced, which is an extremely interesting system, and also B baryons. And you also get a high boost. These can be produced with a lot of energy, so they fly some distance. And this is very advantageous for time-dependent measurements. And indeed, if you look at the hadron colliders and hadron environments, you see that they have a strong tradition in B physics. You go back to 1977, this was not a collider, it was a hadron beam. This is where the epsilon system was discovered by Lederman. If you go forward to 1987, UA1, this was, it should be said that this was done more or less in conjunction with Argus, which is B plus and minus, but UA1 was able to observe BB bar oscillations. And the rate of these oscillations was the first indication that the top mass was heavy. And then in 2006, the CDF experiment reconstructed these BS decays into BS pi and other things, and with these they were able to actually observe the very, very fast BS oscillations. So hadron colliders have a very rich pedigree and history of making discoveries in B physics. And if you talk about going hadron colliders, there's only one show in town at present. That's the LHC. So here you see this from above. Here's Lac Le Mans and Ring, and the 4 experiments: Atlas, CMS, LHCb, and Alice. Now, the big boys here are Atlas and CMS, and several of you in the room are on CMS. So the next question we want to address is, well, if you want to do this flavor physics, then Atlas and CMS, these are fantastic multi-purpose experiments. Why can't they do flavor physics? Well, they can. Okay, so they are very versatile experiments, and they, as I will show you, they have produced very high quality results in flavor physics. But these results are in rather limited and restricted areas, right? And that's because it's very difficult, as we shall see, things such as the trigger play a very important role. The trigger I will explain. This means that, like Atlas and CMS, they are essentially limited to final states involving dimuons. So I think I'm right in saying that the only really cutting-edge, important experiments, measurements which have so far come out from Atlas and CMS in the realm of flavor physics have involved dimuon final states, because this is something that these experiments can handle. These experiments cannot distinguish pions from kaons, and as we shall see, this is something that you really, really want to do, and not being able to do that puts many important measurements out of reach. So you would like a dedicated experiment to actually, which would have those capabilities, which would open up the way to all the field of flavor you would like to look at. So now I take a slight historical interlude, how this dedicated experiment came about, but I think this is instructive, because it's both interesting and it tells you, why LHCb has the features it has. So already in people were talking about the LHC. The LHC was going to be approved. It was going to be approved to discover the Higgs and supersymmetry. At least one of those two things worked out. So people knew it needed Atlas and CMS or experiments like that, but it was realized that B physics could be done there. So there was a proposal of various ways in which this could be done. So there was a collaboration proposed called Gadget, which was actually a fixed target experiment. The idea was to inject a gas jet into the LHC and see just let the proton beam go through this gas jet, and you would produce a lot of beauty hadrons doing this. Another idea was something called LHCb, again a fixed target experiment. The idea here was that you actually took a bending crystal and you would take the actual halo of the beam and let that go through this bending crystal, and the beam would be collimated in the crystal, and again could impinge on a fixed target in some hole to the side of the beam, and would produce BB bar. So you could produce in these two cases B hadrons put in with fixed target. But then there was a more audacious proposal called COBEX, where you actually collided the beams. So the fixed target's okay, but the cross section is much, much lower. You're at a lower center of mass energy. The environment is cleaner, but you are not producing nearly as many beams. This COBEX experiment, the idea was to actually use the full colliding beam mode of the LHC. Furthermore, the idea was, how would you actually know you had bees produced? And the idea was to actually get a vertex detector and put this actually within the beam pipe of the LHC. In that manner, you could be sensitive to secondary vertices. And this was actually shown to be possible in a demonstrator experiment at the SPS called P238. What you can see the idea on the right here on the bottom. The idea is, again, here you're putting planes of silicon in what are called Roman pots. So this is actually inside the beam pipe in a secondary vacuum. You're getting very, very close to the beams. And then you see on the right, what is produced, the tracks are produced, they're going through the silicon, they're recording hits. And in this manner, it's very easy to reconstruct the tracks back and see where they came from. So you're getting very close to the interaction region. And though here you're reconstructing a single vertex, this was a demonstrator experiment. B hadrons, of course, will fly some distance, and they, in this case, you'd therefore be sensitive to a displaced vertex, and you'd be able to trigger on it and say immediately, aha, we have a B there. And so this was a very, very important, powerful idea of Peter Schleim's. And this, though proposed in this initial experiment, this was then, these experiments were encouraged to come together. And what came out of that was the LHCb collaboration. The LHCb is a colliding beam experiment, not fixed target. So it's just the same as COBEX. It has a vertex detector which gets very close to the actual interaction point inside the secondary vacuum, just as COBEX was produced.
Why do you want secondary vacuum?
Because if you put, so the question was, why a secondary vacuum? Well, I will actually talk about the LHCb vertex detector. Moment. The thing is, well, yeah, what would be easier if you just put the silicon actually within the LHC beam pipe itself, and don't bother in protecting it with anything. But there's two issues. Firstly, the accelerator people don't like that because they worry that your detector is really, really dirty. And it's going to, stuff's going to come off it and pollute the vacuum. The second is you would, what you really need your, you also require that there's some protection around, there's some metal protection around your detector, which will, because as the beam goes through, your detector gives impedance. The beam senses that, so that you need what's called an RF shield, both to protect the beam to stop it getting too much impedance, and also protect your detector. So you need some measure of protection.
Sorry, just on that point, you said that all the three experiment collaboration was going to take based out of from each of them. So most of the concept coming from LHCb coming from COBEX. So which aspect like LHB or gather?
Right. Right. Yeah. Again, asking the question. This interesting historical note. So as I've said, I think the key concept, the colliding beam and the vertex trigger, that came from COBEX. What then did we take from the other experiments? Well, what's very powerful in the gadget experiment was also a calorimeter trigger. So it had additional trigger capabilities which COBEX did not. What LHCb had, I can't quite remember now. But if you follow what's happening at LHC, this idea of using bending crystals, that's actually coming back, and there's some very cute experiments being proposed using bending crystals, but not specifically for beam physics. Okay, so out of this was born, this is now almost 30 years ago, but a letter of intent for the LHCb experiment. And what I also should say, I don't want to milk this historical interlude too far, but at the same time, people were thinking of doing B physics elsewhere. So you know about HERA. HERA was the electron-proton collider at DAISY in Hamburg. The idea was that, well, we could do B physics there also. So this experiment called HERA-B was proposed. There, the idea was to actually take the proton beam and impinge it on a fixed wire target. So again, this was a fixed target experiment. And the hope was that you'd certainly produce quite a lot of Bs, and ideally you would produce enough to be able to reconstruct B to J psi K short events, which are necessary to make the measurement of sine 2 beta, which at that time was considered the low-hanging fruit of CP violation measurement. So this experiment was proposed, this experiment was built, this experiment was operated, but it was a disaster, okay? So why was it a disaster? It was a disaster because what these people were trying to do was amazingly ambitious. So they were looking at, because it was fixed target, their central mass energy was something like, it was less than a TeV. And there you get Bs produced, but not nearly as many as at the LHC, but your background coming from minimum bias is enormous. So you start with a signal to background of 10 to the minus 6. At the LHC, it's something like 10 to the minus 2. So this is 10,000 times worse starting point. But still, the beams were coming at an enormous crossing rate, tens of megahertz. So the actual rate of interactions was very similar to the LHC. So you're talking about an experiment which is much more ambitious than the LHC, but taking place actually 15 years earlier. Okay. So, you know, in my view, this should never have been approved. It was approved and it didn't work, but we actually learned an enormous amount from it because the various ways in which it didn't work were very instructive for the design of LHCb. And just to complete the historical tour, at that time we did have another Hadron Collider, of course. This was the Tevatron at Fermilab. CDF and D0 were running there. There was an idea coming from Sheldon Stone and Joel Butler. You remember Joel Butler if you were on CMS. But to build a dedicated B physics experiment. This is something which looks very similar to LHCb, though it has two arms. We'll see LHCb in a moment. Had very nice features. Some of these features have been adopted in future plans for LHCb. This experiment, you know, it was given first stage approval in 2004, but soon after, due to budgetary reasons, this was cancelled, and people on BTEV came over to CERN. Okay, so that's the historical tour. So now let's talk about the key features of LHCb. And again, I don't want to do this from the just perspective of someone telling you, you know, how great my experiment is. I'm doing it from the point of view of, you know, understanding if you want to build an experiment to do flavor physics in this extreme environment, what features do you need? Why does it look like it does? Okay. So this is LHCb. So firstly, it looks like a fixed target experiment. You know, in the early days, when you'd show people pictures of this, they'd say that's a fixed target experiment. You say, well, no, it's not. Okay, so the bees are produced here, and of course some bees go in that direction, and some bees go in that direction. So we only get, we don't get all of the bees produced, but as I will show you, this is the actual designing in this way with a finite amount of money. This is the best way to do it. So the acceptance is unique. The actual choice of luminosity is very specific. The instrumentation is very specific and rather different to Atlas and CMS. And then the trigger. So people of you who are listening on, working on Bell 2, I think this is the biggest single difference. So I'll spend a little time talking about the trigger. Okay. So let's step through these and explain these issues one by one. So firstly, the acceptance. So if you want to do flavor physics at the LHC, how should you build your detector? Well, you should go forward. And that's because the BB bars are produced predominantly in gluon fusion. So the BBs on, despite being 5 GeV, I mean, that's quite a heavy meson, but by the energy scale of the LHC, that's light. Okay, so the two proton beams collide, so you get collisions between two gluons. You're producing a rather light, the beam energies, but the colliding partons will generally be asymmetric in energy. You're producing a rather low mass system, so that system will predominantly be thrown forward or backwards. Okay, so if you want to collect B hadrons, it's advantageous to instrument the forward region. Now, if you had enough money, you would instrument the backward region as well. This is what was proposed by BTEV, but we knew we only had this amount of money, so we got built, and BTEV did not. So this was a wise decision. So but if you decide to go forward, So this is to be contrasted with Atlas and CMS, where your cylindrical detectors, your 4π detectors, and they, of course, the 4π detectors, because you're looking for very massive objects, like the Higgs or supersymmetric objects of a TeV or more. If those are produced, they'll be produced essentially at mass in the lab frame, and therefore they will the decay products will generally go perpendicular to the beam, or at least it'll be a lot of the time they will. Now, if you go forward, there are other advantages. For example, you can actually get very close to the beam line. I talked about the Cobex vertex detector. You're going to see that with LHCb, you can do a similar thing. You can get much closer to the beam than you can with Atlas and CMS. You have high boost. Anything produced in this region, the B hadrons will generally be produced with rather high energy, so they will travel distances of the order of a centimetre. You have a lot of space. You have something like 18 meters to play with in a conventional cavern, and that's actually very helpful, as you'll see, particularly for the rich detectors. And you get it means that if you also, there's, what you mean by high transverse momentum. If you're in the central region, high transverse momentum means 20, 30 GeV. If you're in this region, the bees will generally decay into products with a transverse momentum of 4 or 5 GeV, and this is sufficient to distinguish between the decay products, the B, and the background decay products. The other thing is its operational luminosity. So the LHC is a very high luminosity machine. Atlas and CMS, they want to go to as high luminosities as they could. This is from the run 2, so this is going up to luminosities of a few 10 to the 34, and then you see this luminosity decaying away throughout the film. And the LHCb, you'd say, well, why don't you want to go to those same luminosities? Well, it would be great, but as you go higher and higher in luminosity, then you have problems from radiation damage, and you're getting much closer to the beam in LHCb, your vertex detector, than Atlas and CMS are. So it becomes very difficult to build a detector which will survive at that very high luminosity. Also, at these very high luminosities, you'll get not single interactions happening, you get up to 20, 30, 40 interactions overlapping each other. And that is a very messy environment in which to do B physics. I showed you that event display earlier. So you want to try and make the environment as simple as possible. So going at lower luminosity, then you can do that. So you want to maximize the number of times a B is produced on its own, rather than with lots of other partons colliding in the event. So at LHCb, we go to lower luminosities in Atlas and CMS. In run 2, we went to 410 to the 32. But you have this very nice feature. You see that this luminosity is constant throughout the film. And you do this by leveling. So what you do is that the beams, they initially, rather than let them collide head on, you actually offset them so they are not colliding head on. So that gives you less luminosity than you would have at Atlas or CMS. But as the beam decays away, you make this offset smaller and smaller and smaller, and you control this in a manner such that you get constant luminosity throughout the film. Okay, so you can imagine that this is a very nice environment in which to do physics, because everything remains very, very uniform.
What is the radial distance of the first vertex detector? First layer?
Okay, I'll come on to that, I think, more or less on the next slide. So yes, I've been postponing that. Very, very soon. So I had a question about the vertex detector, which I will seek to answer in a moment. So, okay, so this is how LHCb looks. Here again is the interaction region. This is like 18 meters, and I'm going to just tell you some of the essential features. The first key point is that this experiment no longer exists. And this is the experiment which did physics for run 1 and run 2 of the LHC. this experiment has undergone a very significant upgrade in the long shutdown which we emerged from a couple of years ago. So superficially it looks just the same, but in many key aspects it's very, very different. And I will explain how what those differences are in lecture 4. So the experiment's been upgraded, but it looks superficially the same. But when you look under the bonnet, there are some very, very clear differences. Okay, so let us now try and talk about the essential features, and finally let me talk about the vertex detector. So here we see the run 1, run 2 vertex detector. So what you have, it's made of 2 halves, and each half has it's a succession of planes, and the run 1, run 2 experiment, those planes were, each sensor was half circular. So what you were, therefore, the coordinates you were measuring was an azimuthal coordinate and a radial coordinate. But you have, so you see here in the lab, half of the vertex detector with the plane stretching away. You'll see a little hole in the middle, that's where the beam goes through. And you must imagine another half on top of that, and I'll show you a picture in a second. So how close does it get to the beam? So this was the question I had just now. It gets to within 8 millimeters of the beam. So this is, this gets closer than any other detector at the LHC. And the new vertex detector of the upgraded experiment, in principle, though it doesn't at the moment due to a small accident, it gets a couple of millimeters closer still. Okay, and the idea, you get so close that means you can make the most beautiful and precise measurement you can of the actual decay vertex. So in this room it maybe doesn't come out so well, but this is an event display of a BS, the mu candidate. So a BS, meson decaying to 2 muons. It's an incredibly rare decay, 10 to the minus 9. But you see the decay vertex, and you see another vertex with many tracks coming from it. So that's the primary vertex in which the proton-proton collision happened, in which the bee was born. And then that bee flies over a centimetre, because this is the boost which is provided at the LHC. And then you beautifully reconstruct the 2 muons using this vertex detector. So we can say more about it. So here's a zoomed up. Here you see the planes more clearly. You see the hole in the middle again. So these again, they look like compact discs, if you remember what they are. But with this whole compact discs have a hole in the middle. They look like compact discs. This is the sensitive area. This is the readout electronics. The new vertex detector planes for the upgraded experiment are actually are square, not circular. Here's a measurement of the.
Why is it square?
Because it's a pixel detector. We can talk about that next week. I mean, that's not a that's a small detail. But let me today remain focused. Let me just talk about the experiment from which the results have come. Okay, and what you have to do is, this material is kept as light as possible to try and minimize multiple scattering. So for those of you who care about these things, what your badge of honor on a vertex detector is how well you measure the impact parameter. So that's your measurement of the perpendicular distance from where the track, you extrapolate the track back to the interaction region, and the displaced, if that track comes from a displaced vertex, there'll be a perpendicular distance between that track and where it came from. That's the impact parameter. How well you measure that resolution, and that depends both on the intrinsic resolution of the sensor and also the amount of material you have. So you measure this as a function of 1 over transverse momentum. So as you go up in transverse momentum, which is at the lower region of this graph, you have higher momentum tracks, and they have less multiple scattering, and so in this region you are sensitive to the actual intrinsic precision of the sensors, and this evolution depends on how much material you have. So just take it from me. What you see on this plot is that the simulation and data agree very well. And also, if you compare this with that from other experiments, you'll find that this is behaving, you know, this is beautiful, it's
How
exquisite.
is it managed without cooling? Without cooling, how is it managed? Because
Well, no, there is cooling. Yeah, no, it has to be cooled. So all this region is cooled. And when I describe the upgraded detector, the cooling there, that's a beautiful work of art in its own right, because it has a very thin capillaries through which
Work-based carbon CO2.
yes, but there wasn't CO2 cooling here. Okay.
No electronics. If there is no electronics, then how the readout?
No, there is electronics. This is the electronics here. This is the readout electronics. And on top of it, I don't know if I have a picture. I realise I should have showed you more. Yeah, I should have had more slides on this because I know people have built vertex detectors here. But what you have here, this has the sensors, but then you have on top of these there are metal strips which run over each of the over the sensors, and so they actually read out the sensors and route the signal to the electronics on the outside. But yeah, I apologise. There's obviously much more I could have said about the vertex detector, which I didn't. But here's another slide nonetheless. One thing I should say is that, yeah, so it gets very, very close to the beam, but you cannot leave it there because when the LHC injects, the beam is much bigger and it's wobbling around. And it's only when the LHC will inject, they will put it into collisions and then they will collimate and squeeze the beam. And only then do you get stable conditions. So you cannot have your vertex detector close to the beam in that case. So actually these two halves of the vertex detector move. They are, in injection, they are kept apart by some centimeters, and only when stable beams are declared, they're put very close together. So here's a picture looking down the vertex detector from one side, and this is also this is in an open position. But you see the hole, and you see either side of it. Here you see this. There's this foil which gives you the secondary vacuum. So that foil is kept as thin as possible. It's a beryllium foil which is kept I think 200 microns. But that's needed both to protect the beam from any mess which comes from the silicon, and also to provide some RF protection as well. But you want that has to be as thin as possible to minimise multiple scattering. And to give you an idea, in collisions, the actual this is the actual size of this when it's closed, the size of the aperture, the size of the hole through which the beam has to go. It's marked out in red here, and to give you some idea, that is this is a €1 piece, and maybe you've not seen a €1 piece, but I was looking at something like a 5 rupee piece. It's a rather small, this is a remarkably small hole through which you're asking your beam to go. So, when this was first proposed at the LHC that we want to put our silicon this close to the beam, people said absolutely not. But after many months and years of discussion, we were allowed to actually go into this very, very restricted region.
So, since you are saying this, that people were not agreeable. So is that the audio experiment you say where they have to put this vertex detector very close, that result from that or kind of experience from that?
Yeah, it was all building on this experience. Yes, indeed. But this also, the fact you can do this also requires that the LHC have great control over the stability of their beams. So it's a two-way dialogue. Okay.
what temperature does it operate? -25.
The silicon, the Valo silicon. These are all very good questions. It's Yeah, it's is it -20 or is it -30? I mean, it's in that regime. It's in that regime. Okay. Okay. Yeah, finally, because you're so close to the beam, you worry about radiation damage. Indeed, I showed you this vertex detector. An entire spare vertex detector was built because it was thought that there's a danger that the first one would die through radiation damage. In fact, it didn't. It shows you the efficiency after this is almost at the end of the lifetime of that. This is almost at the end of run 2, not quite at the end of run 2. Red here is red and orange gives you essentially 100% efficiency, and you see that the detectors remained very efficient. I can't explain what's happening in these regions here. So it actually lasted very, very well. This is actually in contrast, and this is also a testament to the developments in radiation hard silicon. When that Codex experiment was proposed 20 years before this was built, then silicon was much less radiation hard, and they said, well, we can build this, but we're going to have to replace it many times during the run. So the suggestion then was that they would actually have to replace the silicon something like every 2 months. Then that would be this complete headache. I mean, what an overhead that would be. So that was not necessary, and it survived throughout 10 years.
So in this specific plot, you see that the efficiency is much larger, closer to the beam height, right?
Well, this plot, the question was, you could see that the efficiency is much closer to the beam height. Indeed, the plot seems to suggest that that I can't explain, because that's the exact opposite of how it should be. So this plot needs a lot more scrutiny, and I probably should have checked that out before putting it up, because you get a lot more radiation closer to the beam than you do at the outside. So
maybe occupancy is folded.
Yeah, maybe it's the occupancy's been folded. Maybe it's been made in a clever manner. Yeah, so this is a very good question, and I've been sloppy to put this plot up without preparing the answer to that. Yeah, the key point is indeed that radiation damage it falls off. I think quadratically as you get away from the interaction point. So the radiation damage is actually much higher, closer to the beam line than out here. So you expect a lower efficiency in here than out there. The plot doesn't seem to show that, and it's maybe with how it's been plotted. But okay, the message is that there was no significant drop off in efficiency. Okay, right. Now the other thing I want to highlight is unique detector. So Atlas and CMS, they have vertex detectors, but not vertex detectors like that. But what they don't have are dedicated detectors for hadron identification. LHCb does. It has these rich detectors. So the rich detector works on the principle of you produce Cherenkov radiation, and that's in a cone, and the angle of that cone depends on the velocity of the particle. So if you can measure the angle of the cone, and you know the momentum, you can determine the mass of the particle which is going through. The components of a Cherenkov detector are the radiator, which is the gas, and then you have the Cherenkov radiation is then focused on mirrors. Here you see a nice mirror, and it's focused out of the acceptance onto planes of. There's another mirror here. Do I have another? No, I don't. But so it bounces off, in general, it goes off a spherical mirror, a flat mirror, and then onto planes of photo detectors, which will detect the Cherenkov radiation. And here you see a plot of the measured Cherenkov angle against momentum. You see the different particle species, muon, pion, pretty much on top of each other, but then kaon and then proton. And those people who are on Bell 2, so here's something I want to emphasize. So Bell 2 has similar detectors, but the real challenge at the LHC is you're trying to you need to do, when these B hadrons are produced, they could be produced at a few GeV, or they could be produced at 100 GeV or much higher. You have a huge spread in momentum. And so if you want to build Cherenkov detectors, riches to be sensitive to be able to tell pions and kaons apart over this large momentum range, that critically depends on the radiator you use. So we tend to use fluorocarbon gases. This is actually, they're not ecologically sound. This is a problem for future experiments, but we still, HEB at least, we have them. But the actual refractive index of that gas determines the separation between how big this Cherenkov ring is, and it determines at what point you actually get the radiation, and then it determines how big the ring is for a pion compared to a kaon.
Sorry, so on this point, just to be clear, you were saying that refractive index of that it can range over such a broad, I mean, it can vary over such a broad range, so that the momentum coverage of the PID will also be
right
accommodated. Like that?
Yes. So what I was going to say. So what we have is, it's why we have two rich detectors, because we have a different gas in this one and this one. This is C4F10. This is CF4, and the refractive indices are different. And in this one, that means that in Rich 2 you get the Cherenkov radiation does not turn on until later. Just drawing on the board here, people in Zoom, but I should have put this on the slide, but you will
Down.
down.
No, there's a
Yeah, there's
bar.
no bar. Near the bar.
I don't know, there'll be long.
I apologise, people. It's not taken. We don't have this in Oxford. I have to do it all manually. Right, thank you. Stop. Now will it stop? Right. Sorry, for those on Zoom, I'm just drawing the Cherenkov angle formula. Cos theta Cherenkov equals 1 over n beta. This is the refractive index. This is the angle of the Cherenkov radiation. So for this to have a solution for a given beta, well, it depends on the refractive index, and so you get no Cherenkov. So for this, so the choice of the refractive index is such that in Rich 1 you get Cherenkov radiation happening at lower velocities, but at some point it saturates, so the rings will lie on top of each other, whether they are pions or kaons or protons, and therefore to separate pions or kaons or protons, you'd like to, at higher velocities and at higher momenta, you'd like to choose a different refractive index that is Rich 2. So for Rich 2, you get at lower velocities, at lower momentum, you don't get any Cherenkov radiation, but when it turns on, then there's a nice separation between the pions and kaons.
And this transition is very smooth in the sense of momentum coverage. You don't see any kind of.
No, it's smooth. There is a transition between Rich 1 and Rich 2, but it's reasonably smooth.
Point will over that. So for the first it is 260 and the second it is 3200 G.
Yes, thank you. Yeah. Okay, if we can maybe turn the lights off again here, and I thank you. So what you have, you can actually resolve pions and kaons from a few GeV up to about 100 GeV. So this is actually remarkable. This had never been done. I mean, Rich detectors have a rather murky history. Things like the Delphi experiment I worked on, it had a very expensive Rich detector which never really worked. This Rich system works very, very well indeed. So here you see on this plot between a few and 100 GeV, This is showing you your efficiency of in red. If you really have a kaon of actually reconstructing it as a kaon, and then in black, if you actually have a pion, what is the chance of misreconstructing the pion as a kaon? And you see there's a big separation between the red and the black. That's good. Red is identification, black is misidentification. You see that there's for both there's two curves here, and that's just because the identification has been done twice with a different cut on the log likelihood, right? So you can make a loose cut or a tight cut. So you should focus on either the open red and the open black, or the closed red and the closed black. But it tells you that you can really tell kaons and pions apart very, very well. Okay, so that's great. And you know, why do you want to do this? Well, in B decays, the Bs will often decay to a final state with kaons or a final state with pions, and the physics of those decays will be very, very different. So you want to separate them. So to give you one example, Chalmers speed decay. So these are decays which happen at a branching ratio of like 10 to the minus 5. Here decaying into two charged tracks. So the B could decay into a pion and a kaon, or two pions or two kaons, or you can have a B0 or a BS doing this, or a lambda B doing this, and then you have the possibility of a proton as well. Each of these decays has its own physics. If you cannot tell these pions from protons from kaons, if you just reconstruct the invariant mass as you see there, you see that you've definitely got those decays happening, but you can't tell them apart. But if you have a rich detector and you can dial up whether you're dealing with a kaon or a pion or a proton, you see you can separate out each of these decay modes, and you can do physics with each of those. So this is made with early data. Actually, so this is very early data from LHCb. So it has a certain level of background, but just
Can you hear me?
yes.
Okay,
Please.
so sorry for interrupting in the between.
No.
So in this current slide, can you please explain the different colors, because it could be this question from the student side. So what are the different colors says? Can you please explain?
On this slide here.
First, yeah, top plot left. Yes.
Right. Okay. So
Yeah, the red, yellow.
yeah, indeed. Okay, I'm going to show you a more recent plot on the next slide. But what you have here is I think essentially each color will correspond to one of the different decay modes, which is then shown around it. Okay, so you have the most prominent one is the kaon and pion. So that's probably what you see here in the red, which is dominating the plot on the left. And then you have I can't tell you exactly which of the others are, but they will correspond to the other modes, whether it's a B0 or a BS, which is higher in mass, and whether it's, or a lambda B, which is still higher, and whether it's decaying to a proton pion or two kaons. But in the first plot, they are being reconstructed under the two charged tracks, which are reconstructed, are being reconstructed under the hypothesis that they are pions. Okay, and that's but in some of the cases they're not, and that's why they are shifted in mass. Also because they are coming from the decays of higher mass particles. Let me go on to the next slide. I think this is maybe this is better labelled. Okay, so this is just a plot from later data where a more careful analysis has been done, and here you see very clearly. So the three cases. So on the left-hand plot, here there's an attempt to reconstruct B to K pi. So we have demanded a kaon and a pion, and we've reconstructed those in the rich detector, and you get a very clean peak. But you get some residual background. Well, BS to K pi, you see that. So that's here. The rich has reconstructed things well. But this is a much rarer decay, so it's just sitting at slightly higher masses. but then you have tiny amounts of background you can barely see, which involve decays where one of the particles was not one of the particles you want, and the Richter said this is not a kaon, this is not a pion, it's been eliminated. Similarly, on the middle plot, you've demanded that Rich identifies 2 pions, and you have a very clear B to pi peak. But in orange, you see a small background coming from the case where one of the pions is actually a kaon, but it's at a very small level because Rich has done its job. And on the right, where you've demanded that there are 2 kaons, and you've reconstructed BS decay K very well, but with a small background coming in blue from BS decay pi, where one of the kaons has been misidentified as a pion. Okay, so thank you. I should move on, but just very briefly, because there is a magnet so CMS obviously has a solenoid, LHCb has a dipole magnet, and then there's a calorimeter system and a muon system, which CMS also has. But the purpose of the calorimeter system for LHCb is mainly in triggering. So actually, let me talk about triggering here, and I'm going to speed on, and so I will skip a couple of slides. So please don't be intimidated by me doing this. But you've had good questions, so I'm going more slowly than I would have. But I just want to make very clear, compared to those of you who work on Bell 2, that we have a very particular problem at Hadron Colliders. So just to put it in terms of raw data numbers, the LHC operates at like 40 megahertz, and it does so for like 15% of the year. The LHCb raw event size is 100 kilobytes. That's about 10th of the size of CMS, but it's still significant. So that gives you 15,000 petabytes per year. To put that in context, that's less than search engines deal with, but it's more than Facebook deals with, or at least when I last looked up this number in 2022, probably it's gone up since then. So you're dealing with the amount of data produced is an order of magnitude larger than Facebook deal with, or at least dealt with. So schematically, this is shown on the right here. This is the amount of data Facebook deals with. This is the amount of data LHCb deals with. But of course, if you talk about money budgets, this is shown in green. This is how much. This is the budget of Facebook, and this is the budget of LHCb. So it's just not possible. We don't have the money. We don't have the time to actually store all that data. So we have to do something about it, and that is the role of the trigger. These collisions are happening at this huge rate, and what should be clear is that most of the interactions we're looking at are not of interest. So the collision rate is something like 40 megahertz, but B hadrons are produced something like only produced like once every 150 pp collisions. And even if a B hadron is produced, they're not all equal interest. Most of the ones which are of interest happen at like 10 to the minus 3, but some are much, much rarer, like BS from mu happens at a few 10 to the minus 9. So if we tried to store all of this data, it'd be stupid, because most of these events are not of interest. So we need to find a way to pick out those events of interest. So this is just the same problem CMS have, but they're CMS. You are mainly focusing on Higgs and rare SUSY searches and things. LHCb, we're focusing on B decays. So we need to look for signatures to do this. So we need to look for signatures of B decays. We want to look for initially something which is a very simple signature, which we can immediately identify quickly. So this is where we look for the actual transverse energy of the decay product. So a B has a mass of 5 GeV. So typically, if you look at that energy resolved transverse to the beam, or the momentum resolved transverse to the beam, if you look at the decay products which have transverse energies of a few GeV, that would be characteristic of a B decay. Whereas background processes tend to be less than a GeV or so. So that's a signature you can identify very quickly in your calorimeters or muon system. If you have more time, which you do at the next stage of the trigger, you then can read out your vertex detector and see tracks and do things with those tracks. For instance, you can reconstruct the impact parameter. So I've taken one of these tracks, reconstructed it back, extrapolated it back to the beamline. You see it doesn't come from the interaction point. This is the finite impact parameter. And this is a signature of the B decay. So in your next stage of triggering, having suppressed the rate a little in the first stage, your next stage you can look for tracks of that sort.
The high transverse energy, what is typical?
What is typical?
Transverse energy.
Yes.
What is the typical value?
What is the typical
Value of the transverse energy?
The typical value of the transverse energy? Right, yeah. Do you work on CMS or?
Yes.
Yeah. So in CMS, when you talk about high PT, you talk of tens of G, because that's because you're in the central region. If you're in the forward region, the high transverse momentum only means 3, 4, 5 GeV. It's essentially the energy scale of the beam meson itself. So yes, it has a different meaning in LHCb in the forward region than you're used to at CMS, because the background processes in this forward region have a transverse momentum of less than a GeV. Thank you for the question. And then finally, if you with a bit more time, you then can actually reconstruct all of the tracks and see if they come from an actual secondary vertex. This, and you can fully reconstruct the B decay. So these are the sort of steps in the trigger where which will enable you to find the B decay, and they're in steps of increasing complexity, so you can do them at different levels of the trigger. And what I want to emphasize is that this process here, we are not demanding that one of the tracks is a muon. As I said, Atlas CMS, they tend to look for B decays into 2 muons. So this example diagram here does have 2 muons. So that is very clean signature. But in general, the process I lay out before you does not require that you have muons. You can just deal with hadrons, for example. So you can reconstruct with good efficiency and trigger with good efficiency on a hadronic final state. And that's something that I'm afraid Atlas and CMS cannot do. So this process enables good efficiency for all kinds of B decays. So LHCb has this trigger system which is dedicated to B decays. It means you can sweep up essentially any decay of interest. Okay, so this is more technical. I'm going to skip over this. I just want to say that we essentially do the trigger in 2 stages. So what we call the L0, which is this hardware trigger, where you look for this high PT signature in either the calorimeters or the muon system. And then if you do, and that suppresses the event rate by about a factor of 40. But if you succeed in doing that, you then read out the event, and the rest of the event goes in the so-called high-level trigger, and that uses a computer farm which looks for these impact parameters and looks for these secondary vertices. Right, so let me skip over those slides. And for moving on, what I want to give you a spoiler alert, the strategy outlined here, which has been very successful, it is also limiting because it restricts the luminosity at which you can run at. This is another reason why LHCb ran at this low luminosity. This trigger system has been changed fundamentally for the upgraded detector, which is being commissioned now, and I will explain this next week. Right. I think at this point, probably we should just go back to Bell 2 and say, well, you talked about the hadron machines and the hadron detectors. What's really different between that and what you do at Bell 2? On this slide, I made a very executive summary, just so Bell 2 people don't feel left out. and to emphasize some important differences. So firstly, there's the geometry. Bell 2 is a 4-pi detector like Atlas or CMS, and that's because at E plus E minus, a very large proportion of the B production happens in the barrel region. So there's therefore you need a very good barrel. So it's not a full detector, it's a barrel detector. Bell 2 has particle identification just like LHCb, relying on Cherenkov radiation. But here it's much easier. And it's much easier because at Bell 2 you're producing the 2B hadrons at rest. And so if anything, as they decay, you know with a high certainty that the momentum of the decay products will be in a much narrower window. You know that you only have to be sensitive to tracks within a few hundred MeV up to, I don't know, 2.5 GeV. So this means you don't need these 2 radiators, you just need single radiators, and you also only need thin radiators. So the particle identification systems at Bell 2 are much simpler than at LHCb. Bell 2, like LHCb, has a calorimeter, but their calorimeter is much better. It has much better resolution, a beautiful crystal calorimeter, first used at Bell, and that's because you have many fewer pi zeros in the event, and therefore you can actually hope to do fantastic physics with pi zeros, so it's much more worthwhile to invest money in an excellent calorimeter. So this is a pi zero peak. So at LHCb, we also reconstruct pi zeros. At CMS, you won't bother doing that. You reconstruct jets, you don't reconstruct pi zeros. But in B physics, you want to reconstruct pi zeros, and you reconstruct it from 2 photons. But the width of this peak is I think it's like 5 MeV or something. It's beautifully narrow, much narrower than at LHCb. And this business of the trigger, which I've been speaking of, essentially that's not a problem in an E plus E minus experiment. You can essentially record everything. Right, I did, what I wanted to do was to talk about, I mean, you've had excellent questions. I was going to talk about spectroscopy for 10 minutes. Should I do that, or are people tired?
I'm tired of other things. I would like these to.
Okay, I'm sorry. I didn't anticipate the richness of your question, so I'll try and give you the brief. Yeah, because I thought after explaining all this, you wanted to hear something about the physics that we've done with it. So this is just the integrated luminosity collected with LHCb throughout the first 2 runs of operation, 9 inverse centibond. So what have we done with this? Okay. So I'm supposed to talk about flavor physics, but here I'm not. I'm going to talk about hadron spectroscopy. And this isn't really flavor, but if you build an experiment for for flavor physics, it will work very well for hadron spectroscopy. Because some of the most interesting spectroscopy states you can reconstruct and study have heavy quarks in them. So what we're talking about here is non-perturbative QCD, not flavor, but it's it's something we have to speak of. So the question I might have asked you is how many new particles have we discovered at the LHC? And some of you may have said the answer is 1, which is a spin 0 boson. That's incorrect. We've actually discovered 73. And 72 of them have been new hadrons. So you see these over time. So the Higgs is not the only new particle we discovered, but it's a special one, I agree. And so plotted here is the mass of all the particles. Now, don't worry, I'm not going to take up the time between now and lunch talking through each of these. What I'm just going to say is a couple of words about one, something which I think is very particular to the LHC, which are pentaquarks. Okay, so let me just say a few things about pentaquarks. So, yeah, you know the quark model was proposed in whenever it was 1964. And the vanilla quark model you learnt as an undergraduate, you make mesons from a QQ bar and baryons from a QQQ. You're already right at the start of the quark model. Gelman and Zweig said, well, there's no reason you can't make baryons from states such as this, a full quark and an antiquark, and mesons from quark, antiquark. So they are colour singlets, so you should be able to produce them. And indeed, so people immediately started to look for those, and it was a great mystery that for decades nothing was found. So this is interesting in itself. But things have been found, and indeed spectroscopy is of great interest to the wider community, whether you like it or not yourself. Indeed, on Bell, the highest cited physics paper is not a CP violation discovery, which has 1,200 citations, but this observation of this state, which is now known as the X3872. This has almost twice as many citations. And LHCb, again, the high cited paper is not to do with lepton universality, but the discovery of pentaquarks, which I will speak of. Every time a new hadron is found, this excites also interesting media coverage in some cases. This is to do with this is an early discovery of ours, the resonant nature of this state. Here's some newspaper headlines from throughout the world. A very alarming one here. I think this comes from Iran about the gates of hell. God knows what they were thinking, but this gets picked up in the media, and not just the media. This Z4430 did this. It inspired a piece of music that was here played at the Montreux Jazz Festival. You can go and you can find this on YouTube. It's quite nice. Focusing on pentaquarks. So this is the idea of looking for a state with 5 quarks, or more accurately 4 quarks on an antiquark. So people, according to Gelman, that they should be out there, and people look for them. Indeed, this is a story which has an ignominious history. For example, in the early 2000s, these are low-energy experiments. So these are looking for states with strange in them, but not with beauty or charm. So I don't know which experiment was first, but one of these experiments found a bump, and the other experiment looked. They also found a bump, and another experiment looked. They found a bump, and they found a bump, and this is how things happen. But then another experiment, which was slightly more precise, came and didn't find the bump, and then with time the bump decayed away. This is what Hicks said about this. The whole story, the discoveries themselves, the tidal wave of papers by theorists and phenomenologists that followed, and the eventual undiscovery is a curious episode. I think that word curious is doing a lot of heavy lifting here. Curious episode in the history of science. So pentaquarks have a rather murky history. However, back in 2014, on LHCb, we were reconstructing a sample of lambda beta J side proton kaon decays. This was to do CP violation measurements. It's a beautifully clean sample. You see it here, very little background. But then if you make a Daleks plot, if you have 3 particles in the final state, so this is a Daleks plot. We'll see a few of these over the coming days. So you take the invariant mass of 2 of the particles, you square that, and you plot it against the invariant mass squared of the other 2 particles. And this tells you about what's happening. I mean, the final state is very clear, but what happens between the decay of the initial lambda b and the final state? Are there intermediate state particles which are living there for a short period of time before decaying? And if you look at this, you see immediately that there seems to be something happening. You see a band there. So if you then take this projection and just look at the projection, this band is what you see here. So you just look at the black for the time being. So you see that there's a peak there. So this suggests there's some intermediate particle between the production and the decay, which is living for a short period of time. And if one considers this is made from the J side proton, so this is suggesting this thing must have a CC bar UUB. Sorry, here in the room, what happened? This is there on my computer.
Just cross that.
Just a minute. Sorry, this is slowing us down more. Okay.
It's okay.
Okay. Right, so this is telling you that there seems to be some intermediate state with the UUDCC bar made components. And that's manifestly, that's exotic, that is not a vanilla hadron. That, if true, would be a pentaquark. But you have to be very careful because you cannot just look at for a bump and say, I found something, because these bumps could be artifacts of other processes. So, for example, it's important to look at the other projections. So here, shown on the left here, we see the kaon proton. So what you see here is you see bumps here, but those bumps are not exotic. A kaon and a proton final state is made by an excited lambda. So these are lambda star states, which are then decaying. You have a whole bunch of those. So it could be that the various combinations of these lambda star states could lead to the artificial appearance of a bump in the other spectrum, which is not actually a true particle, but just an artifact coming from just the kinematics of the decay. So what you have to do is you actually have to build up a model which describes the lambda star resonances very well. This is, these are not very exciting, but you see a fit has been made to a whole bunch of lambda star resonances, up to about 12 or 15 of them. And then you look to see how that fit manifests itself in the spectrum you're interested in, which is the J-side proton spectrum. And that's what you see in red. You see that the fit, which describes all the lambda star resonances, okay, it doesn't actually describe the data very well at all, but what it doesn't describe at all is this peak. So having done that, you convince yourself there's no plausible way you can explain this peak apart from it being an exotic resonance, and that is the pentaquark. And here you see a fit to the pentaquark. Well, interestingly, to fit this spectrum, you now allow for a new resonance, which is a pentaquark. And this is the mass and the width of that resonance. And rather interestingly, the fit actually requires another pentaquark, which you see here in purple. That you don't, by eye, you can't see where that is coming from. There are other projections where you can get an idea why it might be there, but that's something that the fit seems to want. But clearly, let's focus on the spiky one. There is definitely something there. This is, this after 50 years of searching, this is genuinely a state which has 5 quarks in it. I'll be very quick. That was made with a certain amount of data. That's the run 1 data. This slide here advertises why more data is beneficial. We've now added run 2 data to it. So you see that the run 2 data has exactly the same features as the run 1 data. That run 1 was no fluke. But you see that there are new features starting to emerge. And to try and make those features more obvious, let me show you a close-up with a fit. So what's interesting, firstly, on the left is that actually to the left of this big peak here, there's something else which has come out of the spectrum. It was already there in run 1, but as run 1, it just looked like a fluctuation. In run 2, it's definitely there. And so you have very clearly, you have another pentaquark, right? And that's beautifully visible. And then this peak where you saw fitted a single pentaquark previously with more data, you actually just resolves with quite high significance into 2 peaks. And finally, just to complete the picture, this purple peak, which you probably would not be convinced by, because you could not see any reason why this broad peak was needed. When fitted with the new data, indeed, this does not seem to be necessary. So the update to this pentaquark study is that with more data, there seem to be 3 new and narrow states there. These states are exotic. They're 5 quark states. What you might ask is now, what is the true nature of the pentaquark? And if you, there have been huge numbers of papers on this, as there are for tetraquarks. Is this a bound state really of 5 closely bound quarks, or is it like a molecule of a baryon and a meson held together with some van der Waal-like force? We don't know, and theorists enjoy speculating on that. But with more data and making, for instance, measuring the quantum numbers of these states, which we have not been able to do yet, those questions will hopefully be answered, and we'll be able to resolve whether we have the tightly bound states or the molecular states. For completion, this is my penultimate slide. I should say these are not the only pentaquarks that have been found. Actually, rather recently, by actually looking in a big meson decay, but the big meson decay to a J psi lambda and P bar. If you look here at the J psi lambda projection, there's something at the end. This can be interpreted as this is seen with 5 sigma significance. This is a state which would have a quark content CC bar UDS. Okay, so that is a strange pentaquark. Right, thank you for your patience. But I'm sorry that took longer than I thought. These conclusions I don't need to read through. I emphasised, I hope that hadron machines are very exciting places in which to do flavour physics, but the upsilon 4s should not be forgotten, and there's lots of excitement coming out of Bell 2 already. And if you go to a hadron machine, you really need a dedicated experiment. You need this particle identification. These pentaquarks I showed you, it requires identifying protons, it requires identifying kaons. You just cannot do that, I'm afraid, at Atlas and CMS. You need a rich system. And hadron spectroscopy, though it's not flavor physics, it is something which you will always do at a flavor physics facility. But tomorrow I will focus on flavor physics, and I hope I'll keep the time, and I will talk about the unitarity triangle and CP violation measurements. So thank you for your attention.
So we have quite a few questions from the room. So let us see from the Zoom, because yeah. So people.
Yes, there is a question from Prole.
Yeah, Prole, please go ahead.
Yeah. So thank you, Professor Wilkinson, for this nice talk. And sorry, I'm not from the field, but this may sound quite mindless question about the pentaquark. You mentioned that I mean there are 4 states and so on, but how do you distinguish between, let's say, some bound states and then some of these some, I mean, can you go back to the slide?
Yes. This slide maybe.
3 states. I mean, if you just consider, I mean, you have already mentioned in the two of the pictures, cartoon diagrams, you have
tightly bound
and then molecular model.
Yes.
I mean, how do you distinguish?
How do you distinguish between them? Well, the first thing to say is that maybe something in support of the molecular model is you see on this diagram, there are dotted lines which are actually the thresholds of here, the sigma c and the d0, the sigma c and the d0 star. So these states which are drawn here are very close to the threshold of this of a baryon and a meson together. So this is already pointing slightly towards the molecular model. But the people who construct these models, and I'm certainly not one of them, that they will also say that their model will tell you that they make predictions about the quantum numbers, the spin and the parity of these states. So one thing which is essential is to measure the spin and the parity of these states, which you can do with more data, because you then, with more data, you can leave those as free parameters when you fit these so-called amplitude models to the final state, and the kinematics will tell you what those are. So that is one piece of information. But then the various models, they will also, depending on which model you favour, that they will predict additional states at various places. And I can't remember exactly here where we should look, but the various papers will make those predictions, so you can go and look for those, right? And then there's other things like whether, I mean, these are here seen in the decays of lambda B baryons. Perhaps these states could be produced promptly. So maybe at the LHC, what's to stop them being produced directly in the PP collision? And the probability of them being produced directly in the collision, again, differs from whether it's tightly bound or the molecular model. You might imagine, because the molecular model, if it's a molecule, they're rather loosely bound, so you might imagine it's hard for them to be produced in the fireball of the initial collision. You might even go and look in heavy ion collisions. So there's many signatures, none of which would be completely unambiguous. But if you make all these measurements, then you will favour one model or the other.
Okay, thank you.
Any other questions?
Anyone else on Zoom?
I have a question.
Yeah, please. Who's it, or Qadir, probably?
Saurabh.
Yeah, please go on. Go on, sir.
So when we discover a new state, how do we verify that it is not just a typical QQ bar or QQQ and it's an exotic state?
It depends. Good question. Well, firstly, it depends what it decays into. So if you have a firstly, like J psi proton, if I have a narrow peak for J psi proton, just because knowing the quark content of J psi in a proton, that has to be 4 quarks and an antiquark. There's no two ways around that. So the only other explanation of having this peak here would be, as I tried to explain, but probably too briefly, because you could imagine that in this spectrum, structure could be artificially created, just because what you're seeing is not a genuine resonance, but it's just the accumulation of structure, which are somehow a side effect of the other particles which are naturally being produced. So if these add up on top of each other in an unlucky manner, you could generate something that looks like a state. So by trying to fit here for all possibilities and failing in this fit, as you see, the fit very much fails, you know that conventional physics cannot explain that. It's also very unlikely to be the explanation if the state is narrow, as it is here. And you can also look for other things, which we did do, I've not shown you here. You can actually look for a phase variation across this state. In the Argand plane, you expect, as you go across a resonance, you expect the phase to change through 2 pi. So there's a bunch of checks you can make. But the first check is to actually look at the quark makeup of the state here. And a J psi proton, that is manifestly, the quark content of that, if it's coming from a single particle decaying to that, it's manifestly exotic.
Any other questions from Zoom?
Yes.
Okay.
Do you hear me?
Yes, Sanchal or Sanjida, who's it?
Recording stopped.
Sanjida.
Yes, Sanjida, go on.
Yes. So I would like to ask, like, why is the calorimeter always the most important part of the trigger?
Why is the calorimeter?
Yes, it is always the most important part of the trigger.
Okay. Well, I didn't want to quite give that impression, but it is important. Okay. So, as I said, the trigger system, you go through various levels of complexity. So we look for 3 signals, 3 signatures in a row. So and the initial signature is the one you can do with the least information. So it's the crudest signature, but somehow it's the most important signature, because if event does not pass that signature, then you discard it. So just to repeat, the crude signature, the simple signature we're looking for here is what we call evidence of high transverse activity. This is defined, high transverse is defined in the LHCb manner. So what we're looking for is evidence that an object of the mass of a B meson has decayed into a handful of charged tracks, or indeed neutral tracks, right? So this is what this signature is. And those tracks could be muons, and that's you can identify muons very cleanly. And this is a signature which we do exploit. But we want to look for hadronic decay modes as well. So there's many decay modes of interest where there's no muons involved. Now you could you say, why don't we just look at a charged track and reconstruct the momentum of the charged track? This would be very nice to do, but at this earlier stage of the trigger system, that would take too long to do. So you need a simpler signature than that. So that is where the calorimeter comes in. So you look for a cluster in the calorimeter, and just you can measure the energy of that cluster very quickly, and knowing the location of that cluster just through geometry, you can turn that into ET, a transverse energy. So the calorimeter gives you a very quick indication that there is a hadron in the event coming from a B decay. So in that sense, the calorimeter is very important. Yeah.
Okay, we're getting close to the launch time. Any more questions from the Zoom, or otherwise we'll go look at the room? We have quite a few questions here. So just someone is saying in the chat.
Yeah.
Okay, so thanks, Sanjita. We took your questions. Anyone else on Zoom? Otherwise, anyway, he has a few more lectures. So
yes, and I'm sorry that went on so long.
Right. No problem. I mean, it's very interesting, and there's lots of questions in between. Yeah. So we have quite a few questions, but if anyone has the last question from the room. Right, I think all are hungry.
Yeah.
So let's thank once again, guy, and
Thank you.
Bye. Saurabh, if you have recorded, can you just share the recording with me? I did not record it.
Sure, sir, I will share it.
Please, yeah.
So, is there any possibility for changing the date for Thursday?
Oh, Thursday is not possible
Because
and so it's a bit, the date, of course, we have, I know that you have lecture, so it is a particular school.
Oh, I'm sorry.
So all I can guarantee, we will record the lecture.
I can also send you the slides as well.
But I think for them it's more like lecture is better. I mean, sort of listening to you rather.
Okay, thank you.
So one thing is, which class you have?
We have our class start from 9:30 now, and at 9:30 to 11 we'll have probability and statistics. Followed by QFT, followed by ED. I'm sorry, like this is I'm bad. Okay. So the lectures tomorrow is the same time, 11 second.
Yeah. No, we'll obviously record it, and also the slides will be available.
It will be available.
So what I do, we'll make an Indigo page. We have Indigo, so we'll upload the slide as well as the recording there, and I will send that to the list.
Thank you.
Okay, thank you for your interest. Sorry it took so long.
Okay, so we had okay, so let's quite a few